Today we'll cover two of our recent works, blend and airlift. So I'll start with blend and then I'll move on to airlift afterwards. You can ask your questions in the YouTube chat. I'll try to check the chat and then answer your questions if there are any. So with that, I'll get started. As I said, I'm going to first present blend today. Blend, a fast, memory efficient and accurate mechanism to find fuzzy seed matches in genome analysis. This work was published in Nucleic Acid Research, Genomics and Bioinformatics this year, and it was also presented at the RowHammer conference a month ago. This is a collaborative work with ETH Zürich, our software research group, Carnegie Mellon, TU Delft, and Bilkent University. So let me quickly cover a basic background on genome analysis. So as we know that the high throughput sequencing machines extract smaller fragments of the original DNA sequence known as reads. So the challenge is usually to perform genome analysis from these small random pieces of genomes, because the main challenge is that we do not know where the origin of these reads are in the actual genome, and the goal is to figure out their origins in their corresponding genomes, so that we can essentially complete the puzzle of genome assembly or read mapping, as we covered in the previous lectures, so that we can analyze that particular genome of an individual. And there are several ways of basically finding the origins of the reads, which we will refer to as also identifying sequence similarities between a read and a genome. And the first approach is known as mapping reads to a reference genome, or read mapping. So in that case, we have a reference genome, which is a representative genome of a particular species, for example, a human genome, human reference genome. And the particular reference genome is known to be accurate and potentially as complete as possible. And what we do is that we map the reads to a reference genome to find the potential matching locations in the genome. And we can also identify the differences between a read and a reference genome. So those differences could potentially be unique to an individual, leading or allowing us to find some signs to identify mutations in the individual's genome. So the second approach is to overlap the reads to each other to find similarities between them. So, for example, like here, we may have some similarities between in the overlap region of the reads. So this enables us to construct the de novo assembly of an individual without mapping the reads to a reference genome. So when we were mapping the reads to a reference genome could be considered as a backbone, as a clue where we can look at to identify where a particular read can belong to, or where it may be originating from its corresponding genome. But in the case of de novo assembly, we don't have such a backbone. Rather, we map the reads to each other so that we can essentially construct a genome from these overlaps by extending the reads from their joins, from their overlapping regions, essentially. But in any case, what we find is that the similarities between sequences must be identified, whether this is between a read and a reference genome or between reads. And to facilitate a practical search among many sequence pairs, we essentially want to do it as efficiently. So if we cannot do it efficiently, then you should imagine, for example, mapping a single read to 3 billion different regions in the reference genome, in the case of human reference genome. So it would be extremely inefficient to do so. So to facilitate a practical similarity search, for example, between a read and the reference genome, for example, a reference genome, as I said, can be 3 billion characters. What we usually do is that we build a index structure, which is usually based on a hash table data structure that includes k-mers or subsequences of fixed length k, let's say, from a reference genome, where we also store the locations where these k-mers appear in the particular reference genome. So this is useful because we want to quickly identify the similar regions between a read and the reference genome, and we can use this particular hash table to do so efficiently, usually in like 3 steps that we follow in read mapping. And the first step is the seeding step. So in the seeding step, we determine the potential matching regions in the reference genome between a read and the reference genome. So as I said, these are the locations of these particular k-mers that where we see them in the reference genome, and we then extract those k-mers, again the same length k-mers from reads, and then we query these k-mers in the hash table. So such a query can tell us where these particular k-mers exist in the reference genome, so that we can focus on these regions to continue our sequence similarity search, rather than going over the entire reference genome. So now, like, we reduced our search space from the entire reference genome to these particular regions that we call seeds that we find after matching the k-mers, let's say. And we can also apply further filtering techniques such as chaining or pre-alignment filtering techniques to prune some of the seeds in the reference genome. So after pruning those seeds, we tell ourselves that these seed regions were actually unlikely to align to a particular read, so we further reduce the search space. And then the next step is usually, but optionally, to determine the exact differences between the read and the reference genome, so that we can identify the mutations or potential sequencing errors within that particular read. So let's focus on how we find these seed matches using hash tables. So let's imagine we have 2 sequences, sequence 1 and sequence 2, and the sequence 1 can potentially be coming from a reference genome, and the sequence 2 can be coming from a read, let's say. And then we can apply some seeding techniques or sketching techniques, let's say, to extract these particular subsequences from reference genome or sequence 1. So after extracting these seeds, we convert them. We use hash functions to generate their hash values. So rather than using the seeds itself, we actually convert them to their hash values. And we store these hash values in a hash table as keys, and the values that these keys would return would be the positions where these hash values or these particular sequences appear in the particular reference genome. So constructing such a hash table is very useful because it enables us to quickly query these particular hash tables to find whether we have a particular k-mer or a seed in that hash table to identify the matching regions between a pair of sequences. So let's go over that step then to query the hash table. So now we're going to focus on sequence 2, and then we're going to apply the same seeding technique that we applied in sequence 1 to again extract some subsequences from sequence 2. And then similarly, we're going to use the same hash function that we used here to ensure that we generate the same hash value for the same subsequence whenever we see the same subsequence. After generating the hash values, what we're going to do is that we're going to query the hash table. So now, rather than storing these hash values, now that like we built the hash table by storing the hash values of all the seeds that appear in the reference genome, we can now query the hash values that we generate from the read to identify whether that particular subsequence also exists in the reference genome or not. And after querying the hash table will quickly tell us whether there's a match, meaning that that particular hash value exists in the hash table, or it doesn't exist, meaning or no match. So this is pretty beneficial for us to quickly reduce the search space, as we covered in the previous slide, to quickly reduce the search space from the entire reference genome to particular regions in the reference genome. And there are some seed matching techniques that we apply in these sequences, because you might have asked yourself that why we're selecting these particular subsequences but not these, let's say. And these are essentially determined by the techniques that we call seeding techniques or like sketching techniques. These terms are usually used interchangeably depending on the particular algorithm that we're focusing on, let's say. So first, seeding technique is as a sampling. It focuses on sampling the overlapping k-mers. So when I say an overlapping k-mer, you should assume that a k-mer is a subsequence of a fixed length k, and the overlapping k-mer would be the next k-mer when you shift the character by 1, and then keeping the same length again. Now like we're shifting by 1. So here we have one k-mer, and then we shift by 1 character, and then we can generate this particular k-mer again from the reference genome, let's say. The overlapping k-mers would be, again, all k-mers of a particular sequence using a certain k value, in this case 7. And the sampling approach, one sampling approach is known as minimizers, and it focuses on picking only a one k-mer in a window of k-mers, so that we reduce the storage requirements of these k-mers that we generate from the reference genome. And the reducing storage requirements would then essentially improve the performance of searching for these seeds, because rather than searching for all of these k-mers now like I can focus on one of these and do the search in the hash table. So this also essentially improves the performance. So in this particular technique, there are two main parameters. One is the k length, and the second is the window length, so how many k-mers that we're going to include. But essentially what we do is that we generate the hash values of these overlapping k-mers, and the goal is to pick the k-mer with the minimum hash value, and we pick that particular hash value, and then we store it in the hash table or query it in the hash table. So the idea behind the minimizers is that when two sequences are relatively similar to each other, then the minimizers guarantee that we're going to generate the same, or we're going to pick the same minimizer k-mer as long as we use the same hash function, of course, depending on the parameters that we pick here. Again, as I said, window length has a huge impact on the accuracy and the performance of these minimizer technique. So let's also look at another seed matching technique known as the space seeds. So this space seed, the goal of space seeds is to allow mismatches at certain positions of these k-mers. So when we want to match these particular k-mers to each other, they will not match because their hash values are going to be different if we were to follow an approach similar to minimizers, let's say. But then the intuition is that these k-mers are still highly similar to each other. Perhaps maybe they differ only by 1 or 2 characters. And the goal is to somehow make these subsequences or make these k-mers match each other by ignoring the characters where they may be different between 2 sequences. And to do so, the space seeds apply a pattern on these k-mers such that some of the fixed positions or some of the fixed characters are ignored. So you can assume that we're replacing the characters at particular positions with don't care characters, in this case, X. So when we do this, even if basically, so let's look at this particular example here. We have C and we have A. So if we convert both of them to X, then they are essentially going to match because, by the way, these are called spaces, because when we hash these sequences, rather than hashing them, when we hash these, then we're going to generate the same hash value because this string and this string are identical to each other. So they should generate the same hash value, although these 2 strings weren't identical. So we somehow, by luck, let's say, we made them equal to each other by applying this particular pattern. So then the choice of patterns, of course, is critical for the effectiveness of space seeds. So now I'm going to cover one last seed matching technique known as linked k-mers or strobmers. And the goal is to allow insertions and deletions as well as potentially the mismatches as we covered in space seeds. Again, like we're now looking at some longer sequences so that we can show you where the insertions and deletions can be coming from between 2 sequences. So in this particular example, these 2 subsequences are different than each other, but if we picked the minimizers from both of these sequences, then we could have actually picked the same minimizers. So this could tell us that these 2 subsequences can actually essentially be similar to each other, but maybe they differ because of certain insertions and deletions. So the goal is to avoid or somehow ignore these insertions and deletions so that we can match these potentially similar sequences to each other. So what we essentially do to enable that is after selecting some k-mers, for example, by applying the minimizer technique, we link those k-mers to each other and then generate somehow, let's say, a compressed string out of these longer strings. So we call these seeds or string strobmers. And rather than hashing these longer sequences, we hash them so that we can generate the same hash value if these selected k-mers are exactly matching between 2 sequences. And doing so, we ignore the potential insertions and deletions that may be happening between these potentially similar sequences. And then we were able to match them. So by far, you might have noticed that whatever the seeding technique we do, at the end, we hash these seeds. This enables us to find seed matches with a direct lookup of the hash values, right? Because rather than storing these sequences, which could be costly to store them in a hash table, we essentially shrink them into the hash values using certain amount of bits, let's say 32 bits. And this ensures us that we're always within a particular space budget when we're storing these strings in the hash table. And the main benefit of using these hash tables is as essentially, as I said, like we can find the matches between hash values very efficiently with a direct lookup of these hash values. And to do so, the low collision hash functions are mainly used. This means that seeds must exactly match to generate the same hash value. So here, in this case, we have the space seeds, and these seeds have to exactly match so that we can essentially subsequently generate the same hash value so that we can match them in the hash table. And of course, using the low collision hash functions are advantages because it makes it unlikely to match the dissimilar seeds, because we would be assigning different hash values for these dissimilar seeds. But there is also one particular limitation of using low collision hash functions, is that the highly similar seeds, or we call fuzzy seeds in this work, are also unlikely to match. Although, so our main goal when mapping the reads to a reference genome or to each other is to figure out where these reads may be coming from, or where their origins may be in their corresponding genome. And when we're exactly matching the seeds to figure out, to reduce the space from the entire reference genome to these particular regions, the exact matches may not be sensitive enough, meaning there may potentially be some other regions where the seeds are not exactly matching, but they are still highly similar to each other, meaning that if we aligned the read to that particular region, we would be still in a particular edit distance budget. So this means that by forcing the seeds to exactly match to a particular region could lead us to generating less accurate results. So I'll cover all these potential limitations or challenges in this slide when matching the exact seeds, when matching the seeds exactly to each other. So the main limitation is it occurs when adjusting the many seeding parameters when we're matching the seeds exactly to each other. The one parameter is the k-mer size. So the question is, should the k-mer be long or short? Because if it was long, then finding the long exact matches is less likely than finding shorter exact matches, right? And the second parameter is, in the case of, for example, minimizers, is the window length. Should it be, again, long or short? So longer windows would provide a better sampling, meaning they would further reduce the space requirement and essentially improve the performance. But then if we sample too much, then we can lose also accuracy. We can miss some seed matches that we would have found otherwise by using a shorter window length. So all these parameters determines, of course, the content of the hash table, which then subsequently determines the performance and accuracy of our genome analysis. So there's always this trade-off between performance, memory, and accuracy when exactly matching the seeds to each other. And now, basically, I'll try to convince you about the potential opportunities of using fuzzy seed matches. So a fuzzy seed matching, to reiterate myself, is to find is to match the highly similar seeds to each other. Not necessarily the exactly matching, but also the highly similar ones to each other. So such a mechanism for finding seed matches can enable assigning the same hash value to highly similar seeds. So in this case, we again have space seeds, but those space seeds, although we applied a particular pattern, they still differ because we actually missed the positions or the character where they differ from each other, because the pattern applies the don't care characters to particular positions without knowing if they differ or not at these particular positions. Here in this case, assume that we're missing the character that these two space seeds are differing from each other, but a fuzzy seeding technique could still generate the same hash value, although they differ from each other, but they are still highly similar to each other, such that we can generate the same hash value and then we can query it in the hash table so that we can find these fuzzy seed matches by just looking at their hash values. And the other goal is, of course, we still want to assign the different hash value for dissimilar seeds, because we want to make sure that we're not really finding seed matches where the seeds are not really similar to each other, right? So we also want to do it with a high performance, meaning we don't want to calculate the distance or similarity calculation between these seeds, right? We want to generate these hash values very efficiently without any distance calculation. And we want this method to be space efficient, meaning we don't want to really generate multiple hash functions or multiple hash tables as usually done in many local sensitive hashing methods to identify seed matches by, for example, calculating the Jacquard similarity or by finding a single seed match in one of these multiple hash tables. So it needs to be space efficient as well, ideally by using a single hash table. So finding useful and novel seed matches that cannot be identified when finding only exact matching seeds can be essentially achieved using these fuzzy seed matching technique. And this also enables us to rethink the seeding parameters to achieve better trade-off between performance, memory, and accuracy. And these seeding parameters would be the camera size and window length and many other seeding parameters. So now that I covered some basics in read mapping and seed matching, I'll now go over our goal. But before that, I'll quickly check the YouTube chat to check if there are any questions that I need to answer before I move on. Okay, currently there are no questions that I can see. Okay. All right. So apparently there are no questions. I'm moving on. So let me then go over our goal in this work. Our goal in this work is to enable finding fuzzy matches of seeds as well as exact matching seeds with a single lookup of hash values of seeds. To this end, we propose blend in this work. So blend uses a hashing mechanism called SimHash that can generate the same hash values for similar sets. Blend then provides the mechanisms for accurate and efficiently converting seed sequences into set of items so that we can use these set of items with the SimHash technique to generate the same hash value for similar seed sequences. So I'll now quickly describe how SimHash technique works with an example. So the goal in the SimHash technique is to generate the same hash value for similar set of items. So we have an example input here, a sentence. Here, this is the example sentence. And where we also have a set of items in this sentence. And the set of items would be the words in that particular sentence. Or you can just assume that the hash values of these words, because what we essentially do is that after identifying the words or the items in the set, we start working with the hash values of these items in the set. So what we essentially do in the SimHash technique is we count the net difference between zeros and ones at each position of these hash values that are represented in their binary form. So I'll basically show it with an example, how we count such net differences of zeros and ones. Here the zeros will be 0 bits and the ones would be the 1 bits. So at each position means that we start with the most significant bit, which is the leftmost positions in this hash value and also in this vector that we use as a counter vector to count net difference between zeros and ones. And what we essentially do is that we count all the zeros and ones here, and then show the net difference between zeros and ones. And if you see a 0, then this would mean that the number of zeros and ones at this particular positions is equal to each other. So the net difference is 0. Here we show the net difference at the least significant bit position, which is the rightmost position. And here we're seeing +2 value. By just looking at it, I can tell that there are more ones than zeros, and the net difference of because the sign is positive. So this is the encoding in the counter vector. If it is positive, then there are more ones than zeros. If it is negative, then there are more zeros than ones. And by looking at the value, I can directly tell how many ones we have more than the 0 bits here. And in this case, we have 2 more ones than zeros. And here we have a negative value. This means that we have more zeros than ones. So why is this important? This is important because we directly use this counter vector to generate the sim hash value of this particular set. So the set again was a sentence, and the items of that set was the words, and we use the hash values from all of the items of this set to generate this counter vector. And when we generate the hash value for a set, we use the counter vector, meaning we use all the items somehow to generate this particular hash value for a particular set. So the advantage of that, the sim hash value is that so for each position in the bit of these hash values, we look at the counter vector result, and if it is plus, meaning if there are more ones than zeros, we assign the corresponding bit to 1, and if it is 0 or negative, then we assign the corresponding bit as 0. So this means that by just looking at this particular sim hash value and by just ignoring this counter vector, I can tell at which positions there were more ones than zeros, right? So just looking at this least significant bit, for example, I can directly tell without even doing this computation that there are more ones than zeros. So this is actually a very important property of sim hash. This is because when we have two sets that are highly similar to each other, this indicates that only a few items between these two sets will differ. So let's go over with an example to exemplify, to show this. So let's assume that we're now generating another highly similar set, similar to our original sentence by changing the word from hash to sim hash here. And then this would indicate that the hash value would also change to some other random value. But it's not really important that we're generating completely random value here, because when we integrate this, when we recalculate the counter vector by again using all of these hash values, what we can observe is that although the values differ, the actual values, as you can see from the previous version to the new version, the actual values differ. Although they differ, the majority results of zeros and ones are likely to not change. Meaning, if there were more ones at a particular position, and if I just change a single hash value, then it is still likely that I'm going to keep having more ones than zero, because changing a single bit is unlikely to change the particular majority voting result. Then this means that if the majority voting of these bits are not changing to each other, then this means that the sim hash value that we're generating essentially by looking at these counter vectors won't change. So what does this mean? And this means that if two sets are highly similar to each other, their counter vectors may be slightly different than each other, but their measured results are unlikely to be similar, meaning they are likely to generate the same hash value. So it's not guaranteed, of course, that they are going to generate the same hash value, but it gives us a chance, let's say, for highly similar sets to have the same hash value. So the challenge here is to efficiently and accurately convert these seeds to a set of items to use with SimHash. So this is where Blend comes into play, let's say. So this is the overview of Blend, and in Blend, our goal is to efficiently find fuzzy seed matches with a single lookup of hash values. And the input that we provide to Blend is a fixed length sequence. So this is a seed sequence. This could be k-mer, this could be a minimizer sequence or a stopmer sequence. It doesn't really matter. So this is essentially an input sequence that we want to generate the hash value from. So what we want to do is that we want to efficiently and accurately convert the particular seed to its set of items, so that we can use it with the SimHash technique, because the SimHash technique takes a set of items as input. And we provide the two conversion mechanisms for that. We call Blend I and Blend S. And after identifying the set items from these seeds, we use the SimHash technique, as I explained earlier, to generate the hash value of this particular seed from its set items. And then we can efficiently identify fuzzy seed matches by matching the SimHash values using a hash table. So I'll now go over the Blend I technique, one of the techniques that we use to identify the set items from seeds. And the goal is to convert seed sequences into a set of items. So here, input is a fixed length subsequence, is a fixed length sequence, for example, a seed sequence. And what we do in Blend I is that we extract all overlapping k-mers of the seed that we call neighbors. So here, this could be one, let's say, minimizer k-mer that we would have picked. Then what we're essentially doing is that we're actually dividing into further k-mers, let's say, to extract all overlapping k-mers from this particular seed. And as I said, yeah, these are called neighbors. And then we hash all of these neighbors and then generate their hash values. So these hash values that we generate from these neighbors of that particular seed sequence are the set items that we're going to use to generate a hash value for this sequence. The another mechanism is the Blend S mechanism. So I'm not going to go over in a very detailed manner to explain the Blend S, because it's pretty similar to Blend I, only with minor difference, which is if we are using, for example, a linked k-mer strategy, for example, a stopmer, then it doesn't really make sense to extract all overlapping k-mers, because there's an information gap actually between these linked k-mers, which are the parts that we do not link in the stopmer seed, let's say, right? So we completely ignore these parts and we only link them. So since there's such a gap, it's not really useful to extract all overlapping k-mers, and it could be sufficient just to extract the k-mers that are linked to generate this stopmer seed from this particular sequence to the stopmer sequence. And this is essentially what we do in Blend S. We extract only the linked k-mers in stopmers. Here in this case is GCTA, for example, this was linked from here, GCTA, to here, and the second link is TTAA, which is here. And we take all of these linked k-mers and then we use them as neighbors. And then similarly, similar to blend I, we hash them and then we generate the hash values of these neighbors. And then we use these hash values as set items again for that particular seed sequence. Now that we identified the set items of the seeds, now we can generate the hash values of these seeds using the sim hash technique. And the goal, again, generate the sim hash value of a seed by using the set items from blend I or blend S. So you can assume that the set items are provided from these two mechanisms, and you can assume that these are the set items that we extracted, let's say, using these two techniques. Then what we essentially do is we do a binary to vector encoding using a SIMD technique. This is because we want to subtract 1 from the counting in the sim hash technique whenever we see a 0, and we want to add 1 whenever we see a 1, so that we can calculate the net difference of zeros and ones at each bit position. Because remember, our encoding was, if we see a plus, then there are more ones. If we see a minus, there are more zeros. And in order to achieve that, we essentially just subtract by 1 whenever we see 0. And then we convert this to their vector encoding because we use SIMD operations to perform the addition and summation computations, let's say, efficiently. And this is what we do. We use all these vectors to do a bitwise summation at each position to generate this counter vector, again using SIMD operations. And then by looking at the signs of these values, we do a decoding to generate the sim hash value of a seed. If there, again, like if this is negative, then the corresponding position, the bit position of the hash value would be 0. And if it is positive, then it would be 1. And then this particular hash value that we generate for a seed would then have all the properties of the sim hash technique, meaning if we have two highly similar seeds, then if you use the same seed extraction technique, a set item extraction technique, which is either blend I or blend S, then the items that we are going to extract from these highly similar seeds are going to be also very similar to each other, meaning then we're going to lead to hopefully generating the same hash value so that we can find these fuzzy seed matches efficiently. Yes, essentially, so we use these hash values with the hash table either to store them or query them. So we're aware that the blend can be integrated actually pretty easily for any seeding technique. So this could be done by getting the sequences, let's say reads, and then integrating the blend with any seeding technique accurately, so that the blend can work with the seeding technique to generate the hash values, to extract the seeds from these sequences, and then to generate their hash values. And then similarly, we can store and query these hash values using the hash tables, as also explained earlier. Although this can be integrated to any seeding technique, we integrate as a proof of work, we integrate it to the minimizer technique. Here, how we envision that and how we implement blend with the minimizer. So we extract all overlapping k-mers in a window of k-mers, and then we use blend I technique for all of these extracted k-mers in a window to generate their hash values. And then from these hash values, we find the minimum one. So here again, for example, the minimum one is particularly this one. Then we store it in the hash table or query the hash table. So here, by doing so, we enable generating the same hash value for highly similar seeds. And if there is basically another sequence with the similar seeds, then it is also likely that we're going to generate the same hash value, although the seeds are maybe differing than each other slightly. So the another seeding mechanism that we use with blend is the stop merge seeds. So we take the stop merge seeds as is, after linking the k-mers, let's say. And then we use the blend S technique to generate the hash values of these stromer techniques. And then we use the hash tables to store or query the hash tables. So with that, I covered all the mechanisms in blend. So now I'll go over the evaluation part. So we integrated blend into Minimap2 to perform end-to-end mapping. In our evaluation, we used real and simulated data sets from PacBio, HiFi, and CLR. So these are accurate and less accurate reads from Oxford Nanopore Technologies and from Illumina reads, which are the Illumina reads are essentially providing short reads. We also used various genomes. For example, we used human genome, CHM13 and the HGO2 sample. We use fruit fly genome, we use yeast and E. coli genomes as well. So we have two use cases in our evaluation. First one is read overlapping, which is providing the all versus all overlapping, which could be used to construct the de novo assembly. And essentially, this is what we do to evaluate the accuracy, completeness, and the contiguity of the read overlaps. To evaluate the read overlapping improvements, let's say, using blend and other tools. And the second use case is read mapping, mapping reads to a reference genome. And we calculate the mapping accuracy from simulated reads. And also we perform structural variant calling and then calculate the accuracy of that structural variant calling as well to evaluate the read mapping accuracies. Before going over these read overlapping and read mapping results, I also want to show the empirical analysis that we did on fuzzy seed matching. So this means that we identified non-identical minimizers with the same hash value, which would indicate a collision in this case here. So then what we do is that we also calculate the edit distance between minimizer k-mers with the same hash value. So those are going to be shown here on the x-axis. And we also calculate the ratio of collisions with a certain edit distance using Minimap2 and blend. So we have Minimap2 and different configurations for blend. Here the numbers are showing how many neighbors that we're including in blend. So the higher values would mean that we're extracting, let's say, more k-mers, more set items to generate a hash value for a single seed. So the goal in blend or in fuzzy seed matching is to increase the collision rate for highly similar seeds. So this is essentially our goal. And here, this figure shows the collision ratios for Minimap2. And here, we almost have a nice Gaussian distribution over here, where the most ratio is around 10 edit distance, meaning we have collisions between minimizers, and these, whenever there's a collision, those minimizers are not really similar to each other because their edit distance are particularly high. And what we want to do is that actually we want to increase the collision around this area so that we can see we have a selective collision in a sense that those collisions are highly similar to each other and there are many of them. And this is what this figure is showing. So we still have, of course, collisions in the case of blend for dissimilar seeds. And those collision ratios are pretty similar to in the case of Minimap2. But what's different is that we also increase the collision rate, especially for edit distance 2, specifically for edit distance 2, which is telling us that we're generating the same hash value for highly similar seeds. So this is essentially our observation. Blend increases the collision rate for highly similar seeds, while keeping the collision rate similar to Minimap2 for dissimilar seeds. So we're selectively increasing the collision rate for highly similar seeds. So this is the read overlapping analysis results, and the figure on the top showing the performance results in terms of CPU time, and the figure on the bottom showing us the peak memory results. Here the y-axis are showing those numbers, and on the x-axis we have different data sets from human genome to fruit fly, bacteria, yeast, etc. And so although Blend provides a speed up, so these numbers are the speed ups or speed ups compared to Minimap2 and MHAP, I'll mainly focus on the results for hi-fi reads. So those are the hi-fi data sets are here, and these are the essentially very accurate reads. And what we see is that Blend provides an average speed of almost 40x compared to Minimap2. And it also reduces the memory footprint by 7.2x. We can do this because we can now improve the critical parameters without decreasing the accuracy, because now we can find more useful seed matches by playing with these parameters. And in this case, we can increase the window length up to 200 and the seed length up to 31 by either keeping the same accuracy or even improving accuracy in the read overlapping case. So this can be done by finding these fuzzy seed matches that the exact seed matching techniques cannot find. For example, in the case of Minimap2. So I'll now show the assembly evaluation results. So these are the assemblies that we generate after finding the read overlaps using each tool. So we essentially show the results for, again, the hi-fi reads, although you can find the results for other data sets in our full paper. Here we have the average identity genome fraction and k-mer completeness. And also on the right side, the largest quantic NGA and NG50 results. And by looking at the, again, the hi-fi data, we see that the Blend generates more accurate and complete assemblies by looking at these particular values, and also it leads to better contiguity usually in most cases. Fuzzy seed matches can lead to finding novel and useful overlaps. So I'll quickly also show the performance and memory results for read mapping. So this is a similar figure that I showed in the previous slide. We have CPU time, peak memory here, and different data sets over there. But now we compare Blend against Minimap2, LRI, we know Map2, SCON-LSH, and Stop-Align. So what we see is that, again, Minimap2, Blend provides an average speed up of 1.7x compared to Minimap2, and a similar peak memory usage across all data sets, not necessarily on the hi-fi data set. And what we see is that the computational cost of sequence alignment slightly hinders the benefits of fuzzy seed matching, because the sequence alignment is also a very costly step in genome analysis. So we also do structural variant calling using the read mapping results that we generate using Blend and Minimap2. So what we do is that we use Sniffles2 to call the SVs from HGO to long read mappings. And we use TrueVary to compare the resulting SVs with the benchmarking SV set, which are the tier 1 set from a Genome in a Bottle benchmarking suite. And we compare Blend with Minimap2, LRA, and Minimap2. And this table shows the true positive, false negative, precision recall, and F1 values for each tool. And overall, what we see is that by looking at the F1 score, which summarizes all these accuracy results nicely in a single value, it shows us that the Blend can generate the best overall accuracy in downstream analysis when doing SV calling using the hi-fi HGO2 long reads. So I'll now provide the summary of Blend. The problem that we're trying to solve is is finding exact matching seeds introduce limitations in further improving the performance and accuracy of genome analysis. And our goal is to find fuzzy seed matches as well as exact matching seeds accurately and efficiently. For that, Blend provides the effective mechanisms for converting seeds into a set of items so that we can use them with the sim hash technique. And we use the sim hash technique to enable generating the same hash value for highly similar seeds to find fuzzy seed matches with a direct lookup of hash values. The key results that we show is we show a significant speed up and lower memory footprint, especially when using hi-fi reads, and Blend can improve the accuracy of important applications in genome analysis because of finding novel fuzzy seed matches. Now, Blend is published in Nucleic Acid Research, Genomics and Bioinformatics journal this year. So this is the QR code that you can use to access the paper. This is a full open source. And we have our source code as well. This is the QR code to our source code. So with that, I'll now complete the Blend presentation and we'll switch to Airlift.